Hi guys. In this next case, we're going to take a look at linear versus exponential models. So we'll differentiate between the two. We'll take a look at what they have in common, or I should say what separates the two of them. They don't have much in common. And then we'll take a look at applying it towards a problem. Which model do we think works better for a given case? And it's not just 50-50. We want to have some explanation behind it. So let's talk about the two first. Linear functions versus exponential functions. So with linear functions, what we started off the year with, what you've seen in years past, we're talking about lines that have a constant rate of change. I'm just going to use ROC for rate of change. In other words, they go up by the same amount. That's what we refer to as slope. So when we say something like the slope of a line is 2, that means for every time the x value increases by 1, the y value will consistently increase by 2. It's the same thing over and over again. That's why it creates a line. That's why we could use that pattern to plot our points. In real world problems, where do we see linear functions? Anything that, once again, exhibits a constant rate of change. Saying like, in a taxi, you pay 50 cents per mile. Every mile, you're paying an additional plus 50 cents, plus 50 cents. And there's obviously limitless examples you can come up with. But that's what we're looking at for linear. For exponential, we have a non-constant rate of change. So we can't define slope for an exponential function. We could use things like average rate of change, but there is no formal slope because for an example, take a look at the general function 2 to the x power. One of like the first ones you start off with exponential functions. When you start off this function, its y-intercept is 1. But then what happens as the x values get larger and larger? The y values are going up an increasing amount. We start off going up just 1, then we go up 2, then we go up 4, and so forth. And obviously, it would be even more extreme if we continued this. So you could see the rate of change is not constant all of a sudden, whereas with linear it was. But what we do have, and this is what some people confuse as being constant, we do have a constant or some number we're multiplying by, constant ratio. Obviously in the case I put to the right there, your ratio would be times 2. In other words, some form of multiplication. An example. Something like times 2. Percentages are obviously, if you say like, hey, a 2% increase in salary or 2% increase interest rate at my bank, those are different ways of multiplying by something, but it's still a constant ratio. You're multiplying or you're taking a factor of some amount. So now that we know the difference between the two, let's take a look at this table. We have bacteria growth, we have hours as our x variable, and the number or the population, I guess, if you define bacteria as population, in the second column, or the bottom column, I should say. So which one works best here? Well, what I want to take a look at, because it's not clear to me just looking at it, what's going on as the x values increase. So it's clear that x is increasing by 1. But what's happening to the y values? Let's look a little bit closer. It looks like here we go up 80. Here we're going up 130. Here we're going up 190. And here we're going up 315. Yeah, 315. Okay, so right away, and based on what we talked about below, which type of function do you think works best here? It's not going to be exact. It didn't say like write the equation or some exact model, but just generally, which one do we think would be a better idea to use? Based on what we said, I would believe a exponential function to be the better choice. So why? That's part of the answer as well. Anyone could guess here, and we're not going to award any credit for that. So why an exponential function? We can refer to the rate of change. We could say the rate of change is changing. That's a little wordy. I could phrase that a little bit better. The rate of change is consistently increasing. We could say things like it's not constant, it's not staying the same, therefore linear, a line where it is the same, probably wouldn't be a good model. If we were to graph this or think of a graphic representation, a line would just continue on, whereas this might skyrocket up 5, 6 hours. We're already in the thousands, whereas a line would be a little bit more slower or slowly growing. So anything like that would justify your choice here. Non-constant, the rate of change is different. You could even go as far to say, if we want, we could do like 240 over 160. And you'll see it's around, it doesn't work out exactly, but we could say it's close to being multiplied by 1.5 each time. If you do it a few times, it is rather close. It's 360, we have 370. So it does about model a form of multiplication. Any of those would be good justifications here for using an exponential function. So hopefully this helped you separate the two types of functions, and we were able to take a look at a specific case. So thank you for watching. If you have any questions, please feel free to comment or reach out to me by email. Thank you.